Thank you, Reena, for the invite. So, quick introduction, myself, Nitin Sharma, Associate Professor at NC State and UNC. Before I start, I had to disclose that I have equity in a startup we started in Biomedical, with the goal is to translate new electrical stimulation devices. So I'm going to talk about devices today. So unlike insurance or medical drugs, so it's going to be all about devices. So how this is useful for people who have MS or TM. I'm in biomedical engineering. So the idea here is like we are basically researchers. We are innovating new devices, for example, and we collaborate, let's say, for example, with Dr. Wasserowski. And the idea would be like together we can come up with some device, and then we ultimately want to translate. So just a background where we are located. So myself, I'm in Engineering Building 3 in the Centennial campus in Raleigh. We do have some faculty, actually half our faculty sits in the UNC campus as well. So they have this Mary Ellen Jones building as well. So half of us in Engineering Building 3. So more engineers are over there and more scientists, I would say, are here on the UNC side. Biomedical engineering as such is a pretty big field. They are researching into tissue engineering. They are researching new drugs. They're researching new imaging techniques. So myself, I belong to what we call rehabilitation engineering. So we are designing systems that can restore limb function, for example. Okay. So here's the thing gone.
Sorry.
So title should be drop foot. So I'm looking at right now the drop foot problem in which people we have who have stroke or MS or spinal cord injury. Usually the one symptom they observe is like they cannot lift their ankle up. So basically when they're walking, they are like dragging their foot while they're walking. So what happens because of that is when they're walking, the gait becomes slow, unnatural, and there's also the risk of falls as well. So usually when they walk, they have to circumduct around themselves when they're walking. So the way to fix that is so this is what we call functional electrical stimulation. So functional electrical stimulation is a way of sending electrical pulses to the nerves that are hopefully still there. And when we externally stimulate them, they can make the ankle go up. So that's electrical stimulation. So it's a device from Bioness or Walk-It. They sell this device. It wraps around your knee. And then the two black things with the red that you see are the two electrodes that send electrical pulses. So then they go around the nerve right below, like on this side, it's called the fossa, where when you stimulate, it makes your nerve to send signals and the ankle goes up. So the issues with these devices are these are usually, the way they're designed is they're trigger based. So if you're walking, the intensity is pretty fixed, and usually you cannot tune like online to say like on the fly, if you're walking, you can't tune them. It has to be, it's already predetermined, it's fixed. And so for example, one idea would be like if I am walking, if I see my red foot is the way it needs to clear the ground, the stimulation basically is a form of some kind of it ramps up and then it's stable and then it ramps down. So during the ramp up phase when I'm about to clear the ground and then if the foot is up in the air, then the stimulation is maximum. So this stimulation intensity is fixed. It's not changed at all. So electrical current that's going in, is always stays fixed. So there's no way to automatically ramp up or ramp down based on what assistance is required. Okay. So anytime, please do interrupt me. I might go into some slides which will have some graphs and everything. So I might skip out something, but please do ask me if I'm saying some jargon. So here's one person with foot drop or drop foot used interchangeably. So if you look at her left leg, so you can see it's almost she's having hard time lifting it up. So usually the foot just drops, and then to clear it, she has to somehow lift it up. It gets very, very hard. So now what we have designed in our lab is a way to send this electrical pulses using electrical stimulation, and it times it based on the person's model. So without going into detail, so now if you can see the foot is on the right one, the foot drop correction, the foot always stays up. So what we are doing in this case, in our case, is we are, instead of the device that are available in the market, our methods that we are developing, it automatically, automatically decides what stimulation pulse or intensity that should go in. Okay, all right. Here's a slide which I am a little bit scared about how to explain, but I'll go do my best. So here's, if you look at the green things, is the let's say the ankle angle. Let's say I want to keep my ankle angle at certain degrees, and when I play in the ground, I need to reach that green, green angle. Okay, and the blue is the actual ankle angle. So there's a sensor which is measuring the ankle angle. Okay, if I'm able to reach the green graph, that means I'm good. So what usually happens is the input on the lower graphs is it's automatically deciding how much pulse it should send in. It's based on the person's model. What happens is usually what we observe is that as the person's fatigue, and ultimately if you do more and more trials, the amount of that current that the algorithm of computes increases. So if you look at, so now you're getting closer and closer to 1. So 1 is, let's say, some arbitrary number. It could be scaled higher based on number. So our method automatically tunes this stimulation intensity that is trying to go in, which other devices which are out there, they can't do that. They always keep that fixed. So that gives us another problem. It's like, okay, one thing is we are seeing is like it is reaching the maximum limit of 1, but the angle, if you see the blue graph up on the top, is not reaching my green level, to say. So that's because muscle usually fatigues very quickly. So the reason, and that's why these devices don't function very well, because muscle starts fatiguing. It's because it is artificial in nature. So the stimulation we're sending is external application. It's not the way the brain sends the signals to the muscle. So it is artificial, and that artificial nature induces some fatigue. So it gets harder and harder to reach that green signal, green level. That means that it will be ultimately the foot might start dropping back again. So how do we fix it? We are getting into, we are trying to use a new type of sensing technology which is based on ultrasound imaging. And you know about ultrasound imaging, they're using gyno exams and all this stuff. But here we're using this ultrasound imaging to image the muscle, okay? And when I'm stimulating, whatever is going on inside the muscle, I'm quantifying that using those imaging techniques. And somehow I will use it as a sensor to use it in my algorithm to increase or decrease based on if it's fatigue or not. So I'll probably skip this slide. So here's a new, we are designing a device in which we are, person is walking without ultrasound as a sensing feedback. So and we are seeing some improvement. The person's stride length and stride speed starts improving when I use ultrasound as a feedback. So I'm not providing much detail in there how it works and what all signals are. And these results are just, I would say, 1 week old. So we need to do more analysis, whether it's worthwhile or not. But it still looks very promising that we can use ultrasound imaging to detect this fatigue, and as we can ramp up or ramp down my stimulation intensity. So now you may wonder, like, hey, this ultrasound imaging are like big machines that you see in clinics. How come these machines could be used for something portable that person can put in a pocket and then walk with this type of device? So we are working with one of our collaborators in mechanical engineering. So we're designing new ultrasound sensors. If you can see that, these are very flexible sensors that we can put directly on the skin. And this, unlike those probes that you see in the clinic, these ultrasound sensors are very flexible. They can, they can conform to your, let's say, thigh or to the skin very easily. So we are, on this side, you have different type of sensors that we're developing that you can put directly on the skin. They are body conformable. We're also designing special kind of electrodes which are compatible with ultrasound. So multiple things, innovations are going in our lab on this in this direction. So ultimately what we want to do is we want to design a device in which we will have ultrasound, we have electrical stimulation, and maybe a cable-driven exoskeleton all packaged together, and it could be put in your pocket. And you will stimulate your ankle muscles based on how your muscles are doing, to kind of a real feedback. All right, so next thing is Dr. Krysten Lambeth, and she's going to talk about exoskeletons now.
Thank you so much, Dr. Sharma. I think these battery died too. Then one died. So this is one of our participants with spinal cord injury. So I know it's not the same thing, but also a neurological condition. And he has some residual volition in his quadriceps and hamstrings, but not a lot. And the exoskeleton here, it has motors in the hips and knees, and it's helping him walk. So exoskeletons can allow you to do the task like a therapy exercise over and over. The downside is that it doesn't directly engage your muscles, it just supports you, as opposed to electrical stimulation, which does directly engage the muscles. So this is where we bring in a functional electrical stimulation, as Dr. Sharma already covered. This is someone with spinal cord injury, and the electrical stimulation is eliciting leg extension. So we're going to combine these two, and we're going to use ultrasound as a means of measuring muscle fatigue, and we can also use it to measure how much the person is using their muscle voluntarily. So like I said, the other participant had some volition, so we can quantify that through ultrasound. So kind of an overview of how this works is in this top graph, you can see that that's actually as electrical stimulation is being applied from left to right, the muscle contracts more, and you see those really dark red areas where it's expanding a lot. Once the muscle is fatigued, which is the bottom three plots, there's not a lot of motion. So I'm going to cover like a few of our exo projects. So one of them is called synergistic control. It's inspired by the human body uses muscle synergies. These are combinations of muscle co-activation, so using multiple muscles at once to accomplish a motion, such as the image shows a flexor synergy for picking up the leg, extensor synergy for achieving leg extension, and basically you can control these synergies instead of controlling just the individual control inputs. And that helps when you have a lot of working parts with your exoskeleton. As you can see, I have on the left here, I have a ton of muscles with FES, and then I also have the hip and knee motors. So what we found was, if I can get this to play, this is a basic synergistic MPC controller, and I'm going to tune the exoskeleton's behavior by changing basically a penalty on this synergy. So now this person is getting a lot more hip flexion. So that was something interesting to find that wasn't really the goal of that. We were focusing more on computation cost reduction, which means getting the problem to be solved faster. But that was an interesting finding. Then we've got these wearable ultrasound sensors. You already saw these, but this is, I guess, a close-up view of the A mode sensor is basically like a flat surface with only a few sensors on it. The B mode sensor is like a traditional ultrasound probe, but it's on like a tiny chip. So we had, these are just some images. On the right, that's, since the B mode sensor is so tiny, it kind of looks like a traditional ultrasound image, but it's just like a sliver. And that white line, that's actually the division between the person's quadriceps. You have like one on top, and you have three on top and one on the bottom. So we had participants with and without spinal cord injury walking in the exoskeleton at different levels of assistance on a treadmill, and we collected ultrasound data from them and EMG data as well. Oh yeah, I forgot this is a video. And you can actually see a second what's called aponeurosis appear intermittently. So we were trying to model exoskeleton walking, and there are 4 different models up here. So on the left is the one where we're not getting any muscle activity feedback. So no feedback about how much the person is using their own muscle. And the fit, the red is the actual true hip and knee angle, and the blue is what our model is predicting. It's not very good. Once you add, EMG is better than nothing. Ultrasound is substantially better, and the ultrasound plus EMG, using both of those together, works best. This is probably because ultrasound is giving you kind of physical mechanographic information about how much the muscle is moving, but the EMG is giving you the electrical activity of the muscle. And the last project I'm going to talk about is muscle fatigue informed control. So this is like what you saw in the ankle videos, except now we're looking at quadriceps, because that's mainly what we focus on for exoskeleton walking. So we have this controller that will change whether or not it's delivering FES or just using the motors based on real-time ultrasound-derived muscle feedback. Oh yeah, I have these videos. So that is a rested muscle contracting on the left and a more fatigued muscle contracting on the right. So we had participants walk for 6 minutes, and every few gait cycles, it would take an ultrasound image, and then that data would get fed back into the controller and would determine, I know these plots mean basically nothing, but it's switching back and forth control modes. And let me show you what that actually means. So this is a participant with spinal cord injury, and this is the FES only walking. This is actually using only FES, no motors, on the left leg. Right leg is using motors. But you can see it with the FES only control, while it's activating his muscles a lot, the leg is kind of swinging back and forth. And once we add the motors, it becomes a lot more regular every single cycle. So that's a benefit to combining the motors with the FES. And that is the conclusion of our presentation.